Alright, we are today going to be looking at circular motion due to gravity. And you're already familiar with the idea of circular motion due to gravity because, of course, we know that's why the Earth stays in orbit around the Sun. That's why the Moon stays in orbit around us. We know that's why satellites work. But the interesting thing we're going to do today is look in more detail about how that's physically possible. We know it happens, and now we're going to extend our physics understanding of why it happens. So let's consider our large object, say the Sun, and our small object, say the Earth, rotating around it. Remember, this is translational motion. The Earth is constantly, like its velocity is always acting in a tangent to its orbit. If something happened to the Sun, it's hard to imagine what it could be, but if something happened to the Sun, then the Earth would go flying off into space. It would no longer have the inward acting force that causes the acceleration. Now, the interesting thing, and I'm going to come to this side, the interesting thing here is that all satellites, all of these objects, the Earth around the Sun, the Moon around the Earth, rockets or satellites orbiting the Earth are in free fall. And the way this was first described was to imagine an object that was shot from some kind of cannon or other ballistic device, and it would loop up and fall down. And we're familiar with that idea. That happens every time we kick a ball, for example. It goes up in the air and comes down. Now, if we kick it harder, it will just simply go higher and further. But imagine we could hit or kick or launch something so energetically, with so much energy, that as it started to come down, as it started to fall down under the influence of gravity on the other side, it becomes falling as fast as the Earth or the object underneath it is moving away. We call that it curves away as fast as the satellite falls. And so it's difficult to imagine, but if you can grasp in your head the idea that this object is launching itself, and as it reaches the top and it starts to curve back down, that's happening, that falling is happening in a circle. It's causing it to orbit. It's got just the right energy, it's at just the right distance to be able to turn in a circle, to experience the centripetal force, to experience the circular motion. So if we look here, we found, or scientists found once upon a time, that there was a universal law of gravitation. There was a way that explained how these satellites, moons, planets, how they behave in relation to larger objects. And they found that the gravitational force was the gravitational constant, and you're just going to look that up. The gravitational constant, the two masses involved, and r squared, the distance between the two objects. And a good way of thinking about this is what you're looking for there is how strongly the two objects will be attracted to one another. What will be the gravitational force between the person and the planet that they're standing on? What is the gravitational force between the planet and the Sun that it's orbiting around? However, this becomes very interesting for us when we remember that the gravitational force is the centripetal force. And we know the centripetal force is mv squared over r, a variation on ma. Therefore, these two things must be equal to one another. And if you're interested in the mathematics for this, there's a derivation in your book that you can look at. I'm not going to do the derivation for you today. But the net result of the derivation, v squared, the velocity that the satellite has, whatever the satellite is equal to the gravitational constant times by the mass of the large object, so whatever is being orbited, divided by the distance that the object is at. So this here is for a smaller mass that is orbiting a larger mass. This m here is for the large mass. So it's not the mass of the rocket, it's the mass of the Earth. It's not the mass of the Sun, of the Earth, It's the mass of the sun, it's the mass of the larger thing, the thing being orbited. And this gives us the speed of the satellite, whatever the speed of the satellite is. Now, an interesting corollary to this, or an extension of this, is the idea that all orbits, all distances from a large body like the sun have a certain speed at which satellites will orbit it. If the satellite's going slower, it will fall into the large mass. If the satellite's going faster, it will move outwards. It won't be stable at that orbit. And this has interesting implications. For example, geostationary satellites are set up so that they always hover above the same part of the Earth. The reason they can do that is they orbit at a distance, r, which gives them a speed, which causes them to have a time period of 24 hours, the same as the Earth's time period of rotation. So as the satellite falls into the Earth, it stays in the same place over the Earth. And we can also see that's why, for example, an Earth year is 365 days long, but a Mercury year is much, much quicker, because r, the distance from the sun to the Earth, causes it to have a certain speed that it rotates at, and from that you can work out how fast it's going to, how long it's going to take to go around its orbit, once you know its distance. So, we're going to move next on to the way that gravitational fields behave in terms of circular motion.